Hey, everybody, this is Joe Harper with Reformed Truth Through Ministries here for another interview today. And today we are welcoming Brian Dean to the show. Brian Dean, welcome to Reformed Truth Through Ministries.
Thank you, Joe. It's good to be here.
So we are going to be talking about one of our favorite controversial subjects today. We're going to be talking about the flat earth, and we're going to be talking a little bit about, I'm excited to interview today because we're going to be talking about kind of more of the empirical side of flat earth. We've talked about a lot about the biblical side of flat earth on this channel, but I'm really excited to really get into the other side. But before we get too far into that, maybe you can just tell us a little bit about yourself, your background, maybe your story with flat earth, even faith in Christ. I think you said you had a story to tell, so we can just start with some intro stuff.
Sure. I definitely have a numerous testimonies of faith. I'm in the Reformed camp as well. I probably would follow more of a Zwingli camp than a Luther camp.
Sure.
Not much of a holiday guy at all, even a little bit.
Yeah, I don't think Luther would like you too much then.
Yeah, that's fine. I don't believe in infant baptism either. It's another staunch line drawn in the sand there.
I go with Reformed Truth Through Ministry, but I'm a Baptist, so there's a lot of Reformed guys who say, you're not Reformed, but you know what, whatever.
Right. Let Christ sort them out. I'm not here for that.
Right.
So I came to be a true believer, learning about the earth and its real shape. There was a time where I spent a lot of time on looking at like space weather and coronal mass ejections and looking at, constant video feeds of satellites to view the sun closer, to have a greater understanding of the magnetosphere and all this kind of stuff. And I was a super nerd about it. I'd get up at 5 a.m. before I would go to be a carpenter, and I'd eat 4 eggs, drink a quart of coffee, and watch stuff about space weather on this YouTube channel called Suspicious Observers, right?
Right.
And then one day I realized that a guy took a P900 and he took video stream of CMEs here on the surface of the Earth. And he didn't need a satellite that was 150 miles away in low Earth orbit to do that. And that blew my mind. It was like, well, why do they have that? We didn't have to wait 16 years for the GHOST satellite to be produced to be all excited about it. For what? You know what I mean?
Right.
So that's when I really started to question things. And also is when a guy sat me down and, I used to go back and forth with this guy who was another organic farmer, and I was organic farming at the time for a vegetable pharma CSA, and so was he. And we would talk about all the different ways we are poisoned as a society. And we talk about how they definitely have to be hiding something from us on a grand scale because there'd be no reason for it. And we bounce back theories all the time, and I thought for some time it had to do with evolution. It had to be evolution-centered, and I could go on about that, but I don't need to.
Right.
But one day he calls me up and he says, I figured it out. You need to come over. We'll rap about it. I go over there. He tells me the earth is flat. And I'm like, okay. Well, would you care to elaborate? I never heard anything like that before. And then one of the first questions is, well, what about space? So then we're off to watch all these videos about ISS bloopers, right?
Right.
And I know the speed at which things fall at 9.8 meters per second. And if you're falling in orbit sideways at 27,000 miles an hour, you're already falling. And you're floating because you're already falling. You're at a sustained terminal velocity. There is zero force acting upon you because you're at maximum force. You know what I mean?
Right.
You already fell. Nothing can fall faster. So you watch something fall on the space station, and it's like, if you know what you're looking at, you know that it's over. It's done.
Right.
There's nothing can fall faster ever, unless there's force enacted upon it. Right. So that's typically their explanation is, well, there was some force that was enacted upon it. Like, really, it just looked like he dropped it. Are you serious? So anyways, without elaborating too much on that, once I learned that, and then it was to start asking the bigger questions. I started looking at light in a spectrum, and I started looking at the possibilities that I'm under a dome. And I fully believe we're under a dome. I fully believe that we're separated by waters above. And it's not some like Catholic NIV version of like water vapor that separates us from space. No, there's an actual layer there that's beaten out of a shape. It's the firmament.
Right.
And that's fully what I believe. And if you look at colors in the visible spectrum, when light's projected in the deepest water, the only color that can be reflected back is blue. That's
Right.
it. That's all you get. The absence of light is dark. It's the same thing in the ocean. You go deep enough in the ocean, it's dark. There's nothing there.
Right.
So I made that comparison, and it was really hard for me to wrap my head around it. It was probably harder for me to wrap my head around, we're not moving.
Right.
That was really hard for me to wrap my head around, because I was all about it, man. Like, oh, we're chasing the sun 450,000 miles an hour. We're orbiting the sun in an elliptical pattern that speeds up and slows down, in January, and it's amazing, right?
Did you kind of wrestle with that a bit? Was that something?
Oh, I did for some time.
Yeah. Right.
But it took like some real observations for myself where it just kind of kicked in. Like, I remember one day I was sitting in my car, and I'm reading something on my phone, or I'm doing something. I'm not paying attention to my surroundings, and a gust of wind smacks up against my truck, and it shook me, and it startled me. I thought I could feel that subtle change from a gust of wind, and it startled me. But every day I read a science article about how the Earth's rotation is slowing up or speeding, slowing down, doing whatever. And it's all this unfounded gibberish. But if any of this was happening, it'd be observed, and it'd be like when you hear a sonic boom and a report on the news, like, did you hear the plane break the sound, at whatever time of day? Like, I grew up in St. Louis, and they would report that stuff. Whenever a plane broke the sound barrier, it was a thing, and it was reported upon. It was like an observation that people could resonate with. So, like, when there's an earthquake, could you feel the earthquake? You know what I mean?
Right.
But you never get that with your speed up or slowing down from a dumb science article.
Right. So they're claiming that the Earth is constantly doing that, but we don't ever feel that stuff. Yeah. We don't feel that. We don't experience that.
And you can find those articles go out every such way and every format. It's absurd. Once you start looking at it, because they used to just drink up this and be like, oh, that's so fascinating that they can measure that. They're not measuring it. They're just theorizing.
Right.
Whatever something that scientists say, you can chalk it up to nonsense. And it's sad, but that's truth.
It's interesting that you said, you said you struggled with the idea of the Earth not moving, because when I started getting into this issue, that was one of the things that intrigued me early on, because I was in seminary at the time, and I kind of came into it a little bit more from the biblical exegetical side first, which is different than some people, but I kept reading. There's all these verses in the Bible about the Earth not moving, and I'm like, well, everybody's saying that we shouldn't read that literally, and I'm like, if you're a conservative Bible reading Christian, you're supposed to read your Bible pretty literally, pretty straightforward. So yeah, it's just interesting that was some kind of how, like, I think what you're saying is, like, all of us, when you come into this, everybody comes into it a little bit at a time, and there's so much that you got to kind of pull down and build back up, that everybody has different things that catch their attention earlier and then later, and it's a process for everybody. So yeah, I remember when
Matt looked at me and said, "You think you're moving right now?" And I was just like flabbergasted. I was like, "Of course."
Of course we're moving. Well, there's no way to perceive that you're moving. Of course we're moving.
There's also this part deep in my stomach that sunk, and it was like, he's probably right. But anyhow, that did lead me to believe in creation. This whole idea that we're created over us as being something that came into happenstance out of nowhere, because there was just too much to explain at that point. And I delved deeper into that. I learned a lot about astronomy. I'd like to go right into the second question, if you will.
Yeah, run with it. Go. And just so the audience know, the second question is, what are some of the arguments that you would give for us living on a flat stationary plane? So just go ahead and run with it.
Okay, great. So the go-to is always astronomy. It's astronomy because most of the known astronomy was built upon in the second century, in like 150 AD, by Hipparchus. And Hipparchus was a Greek philosopher. He's the father of trigonometry. He invented the astrolabe. An astrolabe is a flat disk that's used for star tracking for celestial navigation, navigation via the stars. He charted the stars better than anyone ever did. And it hasn't changed at all because it hasn't needed to. So everything we know about eclipses and everything was all inherited from Hipparchus. And he passed it down to Ptolemy. Most people know Ptolemy because he invented, well, didn't really invent anything. He kind of elaborated on the geocentric model and basically inherited Hipparchus' body of work and just elaborated on it. And he took what Aristotle said about the concentric circles that the planets travel in, and he elaborated on it. And he made it so that it was more understandable. Kind of like the go-between there.
Right.
So, I mean, you can find hinges, wood hinges, stone hinges. You can find hinges that date back to 4900 BC. And they're built in the Babylonian era, right? You can find these old hinges, and what do? They follow the solstices, the risings and the settings of the sun. They're astrological markers.
Right.
Some of them have viewing points for Polaris, and they're still the same. And that's charted history, 5,000 years, 6,000 years. Stars haven't moved, but we're in an elliptical orbit, chasing a sun, and a moving galaxy, ever expanding against the universe, while we wobble. The wobble kills me.
Yeah, that we're supposed to be. Yeah, the Earth is moving on its axis. But yeah, the constellations. I mean, and you see this if you study, like, take some of these ancient monuments, like the Great Pyramids, and some of these ancient monuments are lined up with the stars. Or if you're just an astronomer, these constellations always come back. They go a full circle orbit and they come back to where they started. And
right.
And what you're saying, just to kind of mirror what you're saying, is that if we were in this heliocentric model that is put forward to us by modern science, the position of the stars would change, because the sun is supposed to be moving in the galaxy, the Milky Way galaxy. We're supposed to be moving around the sun. All the other stars are moving, and we're supposed to be moving on our axis, but that is not what we observe. So that's a really good argument. I think I'm really glad that you brought that one up.
There's this gentleman, I'm searching for his name right now. It's Mark something. He has a very good YouTube channel. He doesn't put out a lot of content anymore. He did a very funny interview of an astrophysicist. And I won't say any more about that because I'd have to look it up to get more details on it. But he really spoke to me when he started talking about carnival rides and the physics behind a carnival ride. So you got to imagine you're on a circle, you're on a big circle.
Yep.
And there's 5 little circles sitting on that circular platform that are spinning as they move around. And on your little circle, you're sitting in a teacup with 2 other teacups, and you're spinning your teacup. And everyone's been on some version of this carnival ride, right? Whether you're at Disneyland or you're just at your local fireworks show. And when you're on the very outside of the circle and you're spinning your teacup and you feel all that acceleration at the same time, you're flying. But then when you're on the inside, you get this uncomfortable, like, wean where you're slowing down, right?
Yeah.
And that's typically 3 motions. But if you just involve 2 of those motions and you map the speeds that we're traveling at, and you think about the space station, you give that some consideration. The space station is said to orbit us once every 90 minutes, right?
Okay.
But it's also chasing the sun at 450,000 miles an hour because we are.
Okay, yeah, okay. I see where you're going.
So 17,500 miles per hour is the steady rate of falling in orbit. And if you consider, like, the elliptical speed and everything else, it's got to speed up and slow down. I haven't mathed it out in a while, but it's a huge amount in 45-minute period. It has to change speeds because how could it not? And you think about that ride, it just has to.
Right.
How are those guys surviving? Like, pilots pass out at 6 Gs. How many Gs is that?
Right.
Oh, they don't feel it because of the fly in the car. Right? That's the global explanation for that. But if you turn the car while the fly's in it and the fly is airborne, the fly slaps against the side of the car. You know what I mean?
Right, exactly.
So
what you're saying is that there's contradictions in in the model that they're presenting to us. You're saying that when you start to really think through what they're telling us and you start to put the pieces together, it's like a Jenga that it's going to fall apart.
Yeah, space is almost special. You get away with things in space just because. I can elaborate on that a great deal, but I don't want to go any further on it today.
It's a tough one because, I mean, when you bring up flat Earth, there's a couple arguments that people always bring up because they've been so indoctrinated into this way of thinking, but space is the big one.
Right.
One of the biggest ones, in my opinion, that comes up is like, how can you say space is fake? How can there not be, like, they always say we have all these pictures of the moon landing. How do you think the International Space Station isn't real? How can you say that, like, we have all these pictures of the Earth? Like, this is like the jargon that you hear again and again and again. So what you're saying is very important to start, because we're trying to make a case to kind of one piece at a time break that down.
Whenever someone says we got pictures of space, okay, give me a photograph. Let me break it down for you. And if they actually present one, I'll look it up. I'll do a Google image search of it. And I'll tell them what visual team is responsible for it. You never get a shutter speed or a light level. What kind of shutter speed can let something come in from light years away at 17,500 miles an hour while it's falling in orbit? Nothing can. That's the answer. It's not real. You know,
right?
Like you read National Geographic, they'll give you all those details for a beautiful photograph. And if NASA was legit, they'd tell you everything about how they did it because they love to brag.
Yeah, they don't.
You know what I mean?
Yeah,
they got nothing to brag about.
Well, you start once you have your mind kind of retrained on this, and you watch the news, and they always claim they got these rovers or drones out in space, but it's always computer generated images. They never show you a live action camera of deep space because they have nothing. They got nothing to show. And one of the last things I'll say about stars, I'm going to forget it, is if you go to an observatory, which is kind of mimicking what the stars is like, it's always a dome shape.
Every time.
Yeah, 100%. Every time. And I think that it's really mimicking the greater reality that we are living under this dome firmament that you were talking about before.
On that note, I'd like to make a couple other observations. If you want to learn more about Hipparchus and what we gained from him, look up what a stereographic projection is, and you can go down that rabbit hole for a while and you can learn endlessly. And that knowledge led to him creating the astrolabe. The modern day version of the astrolabe, there's a military technology developed by the Army called the planisphere. And what the astrolabe and the planisphere have in common is you get the northern and southern hemisphere of stars above one circle with all the celestial patterns necessary for navigation within a season. Because it doesn't change.
Right.
The planisphere is cheap at 7 layers of paper or whatever all screwed together, and you could get the whole diagram if you look it up. There's an Army manual that describes how to make it. But the astrolabe, it's beautiful and it's brass and it's $1,000, and man, I'd love to have one hanging on my wall. They look really cool.
Well, when that YouTube income starts coming in here, I'll get the GoFundMe.
You get the astrolabe?
To get Brian, we're gonna get, ladies and gentlemen, we're gonna get Brian Dean his astrolabe. So send us.
We'll see about that.
Send us your nickels and quarters, and we will very, very slowly work our way up to get the astrolabe.
Appreciate that, Joe. So there's one thing that Hipparchus did mention that I want to touch on, and it's kind of like something that's been inherited throughout all astronomy that kind of made its own deathbed. And it's this idea that all heavenly bodies are infinitely distant. So Hipparchus is the father of trigonometry, but he lacked communication well enough, in the 2nd century to be able to create a large enough baseline for a hypotenuse to be able to triangulate anything with an acute angle. Okay. So in other words, you couldn't be 4,000 miles apart from someone and measure star distance or planet distance or sun distance or moon distance while assuming a flat Earth. It wasn't something that was capable to him. So he made the statement that heavenly bodies are infinitely distant because he couldn't measure them. And that got inherited by Ptolemy, and that got passed down to Kepler, and that got inherited through all astrology. That idea was just built upon and built upon. And this book, Kings to Throne, goes into great detail describing that folly. That's pretty much what this entire book is about.
Yeah.
Now, another thing,
say the author for the audience.
Gerard Hickson. Gerard with 2 R's. Gerrard Hickson, Hickson. The book was written in 1922. And if you read a book that's 100 years old, it'll destroy any fallacy that people will believe the Earth was a globe for 2,000 years. They didn't. That didn't happen until the 16th century, and he mentions it in here.
Right. Yeah.
And people struggle with the idea for a while. Like that, everyone wasn't all in right away. Don't believe that hype.
It's yeah, because I think even they've been moving the goalposts on even what they were teaching like 150 years ago. But
Oh, I
like
agree.
now they're trying to say that everybody believed, like everybody's always believed in the globe, going back to the ancient Greeks. What's his name? Is it the sticks and stones guy, the Greek guy?
Aristophanes.
Aristophanes supposedly proved it, which is
I don't really even know where that guy came from. I hate to be that guy, but I didn't hear about him at all until I was an adult. I didn't hear about him in grade school. They never taught him in any of my science classes. If you're 45 and you learned about Aristophanes in primary school, I'd like to talk to you about it.
right.
I don't think it was taught back then. I think it's a figment of something they created. They just Mandela'd it in there. I don't really know that, and maybe I shouldn't have said that because I don't want to appear crazy, but I don't remember anything about Aristophanes in primary school.
I'll just say one quick point on your point of everybody's always believed it, because I think it's important, is if let's say you read a biography of Christopher Columbus from the 1800s, and they will say, well, the people who like Columbus, they'll say, well, he proved that the earth was a globe against all the objections of all what they would call the stupid flat earthers. That's the history that was taught. And now they've moved the goalposts of the history, and now they're saying, no, like he just proved that the size of the earth was different by going to the Americas, and everybody believed it's a globe. It's like they contradict their old history books, because 500 years ago in 1492, all the theologians and the academics, whatever happened with Columbus, they were all saying, no, that's not true. And so it's just, my point is that when you actually start reading,
Copernican theory wasn't even introduced at that point.
Yeah, he's like
it was 100 years later.
Right. And so it's just, I mean, we could go in circles on all these details, but 500 years ago, the vast majority of the peoples of the world believed that the earth was a flat stationary plane.
I'm going to correct myself. It was 50 years later. I got some dates written down here. So I'm going to try to not be an idiot. Because someone in the comments will be like, oh, the flat earther said it was 100 years apart from 1492 to, 1490 to 1543 or whatever.
Well, they do like to pick you apart. So, yeah.
Yeah, I don't want to be picked apart. So I'm trying to. I also want to touch on something that a lot of people like to talk about. It happened in England. It's called the Bedford Level Experiment. And there's a lot of other experiments. And this one more book recommendation. This is by Samuel Rowbotham. He went by the name Parallax, a pseudonym, however you say that, when he pseudonym. When he wrote, I hardly ever say that word, I apologize. He wrote Synthetic Astronomy. And this is what the revised version of that book looks like. So this is a great read. It's a lot thicker than Kingston Throne. You get through Kingston Throne in a day or two. You'll spend some time studying this one. But he goes into detail about that experiment, the Bedford Level Experiment.
Yep.
You can go and reproduce it today. That's the good thing about science. You can redo it.
Right. Yeah, it's supposed to be repeatable.
Yeah.
Yeah.
That's one thing I encourage anyone watching this video to do is work on creating an experiment. When we get to my fourth question, I'm going to talk a lot about that. So yeah, I think that about covers it for question 2.
And you can maybe you could just, before we move on to the next question, could you just tell everybody what was the Bedford Level Experiment real quick?
Okay, so it's there's a series of flags. It's a 7-mile experiment done by line of sight in a level straight canal. A guy in a canoe goes along with a flag in a canoe, and as his flag passes another flag, which he's next to, he marks it. So here is a 1 mile, 2 mile, 3 mile, 4 mile, 6 mile, 7 mile, and he tracks it the entire way. So what Samuel Rowbotham did is he got into the Bedford Canal with a telescope, and he watched the canoe go for 7 miles in a straight line.
Right.
You should have been able to see it past 3.
Yeah. And so you have this very long, straight canal, and you got the guy who's from behind watching the guy on the boat go further and further away. He's got the telescope.
Yeah.
And I'm just mirroring what you said again, but the whole concept is that if there is curvature, eventually, because you're going to move along the curve of the earth, that you're not going to see that guy anymore. But if we're living on a flat stationary plane 7 miles away, you can still see him. And I mean, and this has been repeated on far larger scales. People can see Chicago from across Lake Michigan.
Right, and that's all 8 inches per mile squared stuff.
Yeah, and then I'm probably stealing your thunder for the next question, but yeah, what people, the point is you can see things that we shouldn't be able to see if we're living on a globe.
Yeah, so basically at the end of the Bedford Level experiment, when you saw the canoe at 7 miles, it should have been obscured by 32 feet of water, roughly. So you should have been able to see it at all. Not even a little bit, not even close.
32 feet. That's a lot of obstruction that is supposed to be there.
Yeah. If I math that right, that's what it is. So let's move on to.
So the third question is
Glober arguments.
Yeah, common arguments against flat Earth. So we did the ones for, now we're doing the ones. You're going to bring them up and then you're going to kind of break them down.
So I do apologize for saying Glober arguments. It's just, I don't want to sit in a camp and make fun of another camp. That's not the idea of this.
No,
I'm not trying to offend anybody.
You're not trying to ridicule. Just don't.
No, there's no ridicule in this. There's all love. Love.
Just don't talk in circles, okay? No,
yeah.
That's just in good taste, a little humor, but yeah. No, put the disclaimer up before the video, but yeah, go ahead.
So the greatest Glober argument of all time.
I do a pretty good Trump impression. The bestest, maybe ever. We'll see.
The best ever. The best ever. It definitely is the hugest ever. Is the appeal to authority.
It's phenomenal. It's phenomenal. I'm sorry.
That's what they got, and it's the we know, we've done that, we've known for 2,000 years. It got proved in Greece in first century, all this kind of stuff.
Right, and I'll just say real quick on this point. I know we're kind of laughing, but like when flat Earth comes up, it always quickly. I mean, my experience has been that the arguments have been you go to ridicule, ad hominem attacks, appeal to authority, and straw man arguments.
Correct.
In a nutshell, basically, is the arguments are this is so stupid that we really don't even need to talk about it, or we shouldn't even have to talk about it. And people have believed this so long that it's stupid to even challenge this debate that was settled at 500, if not even 2,000 years ago.
Pop culture has really defined it in recent years to where you can't even really talk about it at all. But 10 years ago, I wouldn't shut up about it. I've been in this game for a little while now, maybe not as long as some other flat earthers, but it was 10 years ago that I got presented this information and couldn't dispute it. Right. I started thinking about all the different things I've observed and not being able to explain them. And things I talked about that I'd observed in that moment, like how is this even possible? And no one had anything for me. I thought about it later, and it was like, oh, well, this is because the Earth is obviously flat. And I'll get into a couple of those in a couple moments here. Okay. Maybe I should have kept those under question one, but whatever. But yeah, it's the appeal of authority, like we've been to the moon kind of stuff. That's the biggest one, and the straw man arguments. And then refraction. If you ever come up with an observation about anything, the answer is always, well, it was refracting. It's like, okay, great. Through what medium? Because that's how it works, right?
Right.
So, and it's typically over water. And at different times of day, you can observe water levels differently. Do refraction, do humidity, do changes in water levels and the thickness of the atmosphere. You see a straw in a glass and it looks split. That's refraction. You see a haze on the road. That's refraction. You're out at sea and you see the boat flipped upside down and it's like what appears to be 20 feet higher than the water. That's refraction.
Right.
When you observe a mountain from another mountaintop over 100 miles away in a straight line, and it looks like that 95% of the time, that's an observation. That's real. You can't tell me that something is refracting most of the time just because it's inconvenient for your truth.
Right.
I do not accept that. Not at all. Not in the driest climate imaginable. I can go up Colorado Springs, go up to the top of Pikes Peak. $20, sit in a car. Doesn't even take 45 minutes. You get up to the top. You get out. You can see the broad expanse of 5 Colorado Rockies chains of mountains, right? You got the Sawatch Range, San Juan Mountains, all that stuff. You can look all the way up at Long's Peak. You can identify Long's Peak on a good day. It's 120 miles away. And you can look down at the southern end, where Umagachi is, or I'm sorry, Uncompahgre. This is the tallest peak in the southern chain. I believe it's the San Juan Mountains. It's been a little bit, so I haven't referenced this in some time. But you're basically looking at just about 250 miles. And you can lay a level across it.
Right.
Why is that significant? I'll tell you why that's significant. Why is 250 miles significant? And I'm going to jump right into floor with this.
Go for it. Go for it.
I'm just ready. So you have a circle. I don't have anything with a circle sitting around me. Here, I got a circle. Come on. Every circle is 360 degrees. Divide it into a pie chart. So you divide this into 100 equal parts. So you divide 360 by 100, you get 3.6 degrees. So 1% of a circle is 3.6 degrees. Now think about a protractor. You look at about half the soccer ball, you're looking at 180 degrees. 3.6 degrees, 1%.
Yep.
Now that might seem really tiny right now. What's the circumference of ball Earth? 25,000 miles. Divide that by 100, you get 250 miles. So what you should see is a 3.6 degree arc that repeats itself every 250 miles. And that's per percentage.
Right.
So if you can see 500 miles from an airplane, from point to point, or 1,000 miles, you're looking at 2 to 4% of the Earth. You're looking at anywhere from 7.2 degree arc to 15 degree arc. You know what I mean? It's just not there.
Right.
Now think about a high altitude photograph. Think about that big horizontal picture at 120,000 feet above the Earth.
Right.
How far can you see left to right? I mean, if you can see the entire continental U.S., that's about 31 degrees of the surface of the Earth.
Yeah. What did I think when we were talking? What did you say to me when we were talking on the phone before this? Did you say your experience is the proof? Isn't that what you said to me?
Yeah.
Yeah.
I mean, you go right up on. Let's go right up there. Go right up on top of Pikes Peak. Look left to right. Look at 250 miles of documented points above sea level. Right. You're at 14,000 feet, looking at 50 peaks that are, 14,000 feet above sea level as well. I mean, some of them are, staggered in front of each other. Like if you look towards Albert, there's a sea of mountains that you can't see. But the point is, there's at least 15 very easily identifiable points that are 14ers from there that are, popular shape of mountains. You can look left to right, your whole 180 degree spectrum, 250 miles right there in front of you.
Right.
The one in the middle isn't 6,000 feet taller either, and that's the problem.
I mean, there's so many examples that you could give of this. I mean, I'm in the state of Minnesota, and almost every summer, if you go up north to Duluth, I mean, you got Lake Superior, which it's the largest freshwater body of water in the world. So it's a really massive lake, and you go up. Duluth is on a hill, and you go up to the top where Edgar Tower is, which gives you a really fantastic view of the lake. And they got ships coming in and out of that harbor, and you can see them I'm not going to give numbers here because I'll get picked apart, but like you can see these ships coming in and out for miles and miles away. Mm-hmm. Which if you just wouldn't be able to see that, I really, at some point next time I'm up there, should just put a camera out there and just film for a while, because there's just stuff you wouldn't see. And I'm sure people all over the world with different locations, different contexts, when they're honest with themselves, they can say the exact same thing that I'm saying or that you're saying, is that you can just see it. It's the evidence is right in front of your eyes if you're willing to see it.
And all you really got to do is take a P1000 or some similar camera with a good zoom on it that's, with 50 or 60 times, go down to a beach anywhere, rent a boat that has, a good sonar that looks at the bottom of the ocean, knows exactly where you are within, a few feet. Go out a mile at a time and just keep filming them. And all you got to do is get past, I think, 6 miles?
Right.
5-6 miles?
Yeah. I wrote down, so you said it, that the circumference is 25,000, and Google said 24,901. So, negligible difference. And it says the diameter is 7,926. So, the point is that you were talking about the math earlier. What a 1%
Right.
one degree different. The point is we can do the math, and that you should be able to figure out when and where you can see the curvature.
Yeah, apply numbers. Don't apply appeals to authority. I mean, Neil deGrasse Tyson got on TV and he held up a beach ball and said, "We're 2 millimeters above here when we're in low Earth orbit." You didn't give me any numbers that I can work with, Neil. He's like, if you're 2 millimeters above this beach ball Earth,
right,
you will still see a flat Earth. You're not up high enough yet. And he made that statement because no one goes to low Earth orbit that's a normal person.
Right. And so, I mean, yeah, because the only people who are supposedly up on the space station are I guess what we'll call the VIPs. So,
do you know who Auguste Piccard is?
Not off the top of my head.
So he's a figure in science that's worth looking into. He was the first guy to go up in the stratosphere and take measurements of the air, and it was thanks to him that we developed the different layers in the clouds. The thermosphere, the stratosphere.
Sure.
He came up with all those explanations and the relative densities at different elevations. We got that all from him and his observations. And what he did is he was a design build scientist. He'd have an idea, he'd create a design, he'd build it, he'd fabricate it, and he would theorize and he'd go improve things with his experiments. He was the first guy to go into the stratosphere in a device of his own creation. And he was also the first guy to go, I want to say, like 4 or 5 miles deep in the ocean.
Sure.
Yeah. So this is an amazing guy with the same vessel because it was just airtight.
Right. That's fascinating.
Right.
So I think
he goes up there, and this is in Popular Science. This got documented, and this is pre-NASA era. I forget what year he did this. I'd have to look it up. But this is just kind of off the cuff right now. And he observed the Earth as being a flattish disk with an upturned edge. First observation of what the Earth looked from the tallest elevation everyone ever went to. That's what got put in Popular Science magazine.
Fascinating. I wish I was more surprised than I was at this point, but I'm kind of not too.
Right.
So if we're going off of I'm kind of going to question 4 here. If we're going off of their numbers of, 25,000 circumference, et cetera, I mean, how high should you have to be before you're supposed to be able to see the curvature?
Anywhere above a medium not inflicted by another medium. That's it. That's all you need. So you just have to prove there's not another medium that's affecting your line of sight. Or if there is a medium that's affecting your line of sight, you can explain it with the appropriate observation. Like if you can call out refraction in a long distance thing and prove it, that'd be great. Then we would all know what it looks like.
Right. But you can't.
I've seen one globe argument, and it was over a body of water. By the way, distances over the body's water at like noontime, that's a no-go. I mean, you got water evaporating at a constant rate. It's 95 degrees. You're in Florida or whatever, and you're trying to look out over this body of water at a lighthouse or what have you. It's not a good idea because that's when you're going to get refraction, because that's where there's the strongest medium of disruption. There's water evaporating. There's higher humidity levels.
Right.
Go in the morning. Go at night. Or better yet, chart all 3. Chart the humidity at the different times of day. Just observe as much as you can.
Yeah.
So if we make an observation that proves a flat Earth, someone will say, what's the humidity level? Or what time of day was it? Or all these things. How many times did you test it? We got to be ready with all that information. And Globers never have that.
Right. Well, I think Rob Skiba, he didn't experiment. I mean, he kind of dealt with the refraction argument because I think, he took a boat, like did exactly what you said to do. He took a boat, put a camera on the front of it, drove it across Lake Michigan to Chicago, and he pretty much, kept it steady the whole time. And which, if, like you said, if you just do that, you can debunk those refraction arguments.
Right. I saw a similar one where a guy drove a snowmobile with a laser mounted to it all the way across like a 6-mile lake. The whole lake was frozen, and it was as flat as he could have it. And he just drove the snowmobile at nighttime with a laser pointed at it, and he was able to film the laser where it was reflecting on his snowmobile the whole time he drove, and it was in the same area. It didn't go up or down. It was in the same spot as he drove all the way across. And that's one of the better experiments I've ever seen, and those just get censored. And man alive, the censorship I've seen in a decade being in this this camp. Unbelievable. I've seen some really good experiments too. That snowmobile one, can't even find it anymore.
Yeah.
You got to go to Rumble and look around for this stuff. But
Well,
this Canadian guy.
The truth doesn't fear investigation, and yet flat Earth videos, they get pulled down like it's nobody's business. And
Yeah.
I mean, it tells you something. I mean, the skeptics could say, "Oh, they're just pulling them down because we just can't deal with these stupid arguments, this misinformation being circulated on the internet." But people who are intelligent and start thinking through things know that because there's so much misinformation on so many topics on the internet, and they're not pulling all of that down.
Yeah. Meanwhile, we got military documents called "The Propagation of Electromagnetic Fields Above a Flat Earth," and it talks about 3 different ways to create a magnetic field. how to 3 different broadcasts over a plane, not a curve, a plane.
there are military and even NASA documents that you can read that they either state that the Earth is flat or assume or predispose that the Earth is flat with whatever they're doing. And those have been
it says it assumes a flat, non-rotating plane. That's the language. Yeah.
Yeah, that's the language that they're using. And
you can find that for missile ballistics, emergency flight landings, all the things.
Well, landing. I mean, you could probably talk about. I mean, you think about landing planes, and if the Earth is moving, like what landing a plane would. Maybe that's getting into the gravity stuff. But I mean, you think about taking off and landing. Yeah, you're going to go back to a flat stationary plane.
Sure, that was a pretty good segue. Let's just go right into it.
Go for it.
So you asked me to define buoyancy, density, and gravity and talk about it. I'm going to have you guys look at some YouTube links that I'm going to link in the description, or I'm going to pass on to Joe, and he's going to link in the description. One's a 4-minute video, one's about 15 or 17 minutes. And as you get into later examples of formulas for buoyant force, it gets pretty complex, especially when you get to objects floating or objects rising. They pretty much just find ways to eliminate the force of gravity from the equation because they don't have an explanation for it. And I have a better explanation for it, and I'll get to that after I define these principles. So buoyancy, simply in simplest definition, is the tendency of an object to float, whereas density is quite the opposite. Density is the tendency of an object to sink. Those are the very basic definitions. Now, the formula for density would be, density equals mass over volume. Whereas buoyant force equals density times the force of gravity times volume. And I'm not a physicist, not at all, not even a little bit. And I can't explain this stuff like a YouTube video can. But I can make some observations about it. One is being, what is gravity? And then Neil deGrasse Tyson got asked this, and he said, next question. You know what I mean? I can define it very easily. Gravity is an observation. That's all it is. It's an observation of an object falling through the air. That's it. Gravitational force, or force gravity as it is in all these equations, is 9.8 meters per second per second. So it's just d times 9.8, and then whatever the answer is, it's squared, or in the case of a volume, it's cubed. So that's the very basic explanation for what gravity is. It's an observation of something falling through air and nothing else, just air. And they take the observation of what that force is through air, and they apply it to other mediums to get buoyant force of how something falls into water. Right. Water being the best example because that's what's most common. So that's all gravity is. It's 9.8 meters per second, or it's 32 feet per second if you want the English version and not the metric. But no one maths 32.2 feet per second in these equations. They all use metric formulas. They all go with the 9.8 meters squared. So there you have it. Now, my best argument against gravity and having it only be a theory for a force, because, 9.8 meters per second falling, that's an observation. You can call it whatever you want. I think gravity is a poor explanation because once you get to the point where things are floating and you work the same formula, you have 3 G's on one side of the formula, 1 G on the other, and they just all cancel each other out, and I think that's nonsense. Sure. Once you get to about 15 minutes in the second video, you'll see what I'm talking about. And I can't get down with that. It doesn't make sense for an algebraic equation either, because you can't have 3 of something cancel out 1 of something unless it's all valued at 1, and it's all valued at 9.8. So they changed the value from 9.8 to 1 for the sake of the equation. They have it all cancel out because they don't have another way to explain it. And I made some mention of that before very quickly. But watch the video. You'll see what I'm talking about.
Yeah.
So what's my explanation for what's happening? Well, I think it's dielectric acceleration. And that's a process of accelerating charged particles within a strong electric field. So, I mean, everything's a strong electric field if you believe in the ether. We are in an electric field. So dielectric acceleration against a charged particle, you can stick a balloon to the ceiling. You can get a static charge on your finger, and you can push a pencil across the table. You can divert water stream coming down out of your faucet. There's a lot of things you can do with the push and pull of an electromagnetic field on a basic premise. What's the ultimate destroyer for gravitational theory? Well, it's the bumblebee. What's the bumblebee do? Well, it lives within the electromagnetic universe, and it's the perfect resident. The bee doesn't fly. The bee's wings are similar to like the dorsal fins of a fish. It just keeps itself stable.
Sure.
Right? The bee beats a rhythm in its chest, and it floats. How? I have no idea. This is the most understudied thing and non-talked about part of science of everything that's out there is how does a bee float?
Because what you're saying is because gravity is supposed to be this force that's holding us down to the ground, and you're saying that the bumblebee is able to hover in place. So why isn't it getting?
Yeah, I want to see one of these physics guys tell me the buoyant force of a bee while it's falling versus the buoyant force of a bee while it's floating. Because nothing changes with the mass or volume.
Right. Well, it's that's a great argument. That's something that I certainly haven't thought about much before. And well, this isn't the gravity one is an important one because, I mean, once again, if the Earth is rotating like this and wobbling, as you said, and we're going around the sun, everybody says, well, why don't we feel that? That would be common sense. And their answer is gravity is the mystical force that holds everything in place. And we're taught in school that Isaac Newton is one of the most brilliant men in history. And if you don't believe in Isaac Newton's theory of gravity, you're stupid. That's it. So, and everybody always hears that. Well, if you believe in a flat Earth, then it pulls that whole gravitational theory apart. So what you're saying, once again, is it's a really big argument. It's also interesting that you brought up the ether. The last interview I did, which was with the geocentrics actually, but we spent the whole interview arguing for the existence of the ether, because up until the 20th century, everybody in science believed in the ether, and then now nobody believes in the ether. And it's
correct. I mean, how do you have migrational patterns with birds without the ether? How do bees pollinate without the ether? It doesn't make any sense.
Right.
So if anyone that doesn't know this, when a bee goes to a flower and it visits and it pollinates and it robs it of its nectar or what have you, it changes the polarity of the flower so other bees know not to go there. Without the existence of the ether, how is that possible? How can you send something that far away if you're a bee and know not to even go to that sunflower, but to go to the one that's over there?
Right.
It's amazing. The bee is fascinating. It does all these things we can't comprehend.
Right. So
I mean, the National Geographic article, like 2012, I think is when I first read about it.
Yeah, I mean,
the pollination of flowers.
I wonder how they would answer that, because would they say that I wonder what they would say for how like a bumblebee or a dragonfly, like, because they're hovering in place. I wonder how they answer that.
I mean, yeah, I don't know. I've never asked it to someone at the physics major, and I'd love to. But they did a whole experiment with bees with fake flowers, where they would just change the polarity of the flower, and some would attract to the flower, and some would propel it, and that's how they figured that out.
Right.
It's fascinating stuff. Yeah, so dielectric acceleration. Look into that. You can go down. You can learn a lot about that. It's a never-ending field to study that is very understudied. Everything with electromagnetics is. So I think I've answered just about all the questions.
Yeah. Is there anything else you want to chip in, or you think you pretty much you covered a lot, man. You covered a lot in less than an hour.
Yeah. I didn't really want to ramble on with the common flat Earth distance argument for 8 inches per mile squared. I didn't really want to harp on it. That's why I was reluctant to go with the Bedford Level experiment, because there's some preconceived notions by globers about how that measurement is used and not used and abused, and then there's a refraction argument and all this stuff, and people tire of that. So really what I wanted to do in this interview is introduce this whole idea of looking at a bigger spectrum of the landscape from the side-to-side view.
Right.
And introducing the whole, 250 miles is 3.6 degrees, and that's 1% of the Earth's surface. And if you can prove that, then it's over. But you can't. I mean, obviously, we've all seen these high altitude balloon photographs. I mean, just have one notion of if anyone that's a viewer has a photograph from a high altitude balloon anywhere from 90 to 120,000 feet that you can provide that has recognizable landmarks, I would love to have it. If I can prove a 4,000 wide baseline from that high and apply math to it, man, that's all I need.
Right. Yeah, and I really appreciate how you're kind of coming at it from because you do hear, when you get into this space, you do kind of hear the same arguments both ways again and again, and I know a lot of people get tired of it, but yeah, just to recap, you talked about the stars, you talked about how they always come back to their point of, they go in a full orbit and they come back to where they were before. You talked about what we experience, the stuff that you can see that is miles and miles away that we shouldn't be able to see because of the curvature. I think you pretty thoroughly answered the refraction. You talked about what the curvature, and you talked about gravity and buoyancy. So yeah, I mean, I think we covered a lot of ground.
I'd like to make some misnomer comments too, because we have not figured out everything, not even a little bit. The transit of Venus, I got nothing. I have no idea.
Yeah.
What appear to be orbiting moons, that Galileo saw with his 20 times telescope, I got nothing on that.
Sure.
Not even a little bit. And I'm never going to, and that's fine. I'm very satisfied with my mediocrity in this topic when it comes to those things. But also, there's things on the globe side that they don't recognize, that they don't have, like the selenelian, for instance. And that's anytime you have a lunar eclipse where the sun and moon are on the visible horizon. So like the sun's rising over here, you're looking at the lunar eclipse here, but sunrise is happening.
Right. Yeah.
Or inner planets, for instance. They like to say, "Oh, you can see inner planets just because it's just a little bit. You can only see it till 11 o'clock or whatever." Like, no, I've seen inner planets at 1 a.m., dude. Shut up. You know what I mean? It's
well, yeah. Into the selenelian, I always butcher this word, selenelian, even though I do know what it is. Believe
right.
me or not. But yeah, you can see in those instances, you can see the Earth, or I'm sorry, you can see the moon and the sun at the same time above the horizon, and you think about the heliocentric model of what a lunar eclipse is supposed to be, that the Earth is supposed to be in between the sun and the moon. It doesn't make any sense.
And one of the other ones that people like to point out is like, oh, well, the moon is a ball. You can tell the moon is a ball. Okay. Take a ball. Take another ball. Get in a room with one light source. Cast a shadow on the ball and try to recreate a crescent moon. I dare you. You can't do it. And the other thing that is missing from the moon that we never talk about, never see, is there's no specular highlight. Right. Like right here, you got a specular highlight. That's a bright spot because it's closest to the source of light that's over there. I got a lamp right there, and you can see the bright spot on the ball.
Right.
Probably another bright spot from this lamp over here. They added it with CGI to the globe photo.
Well,
it's that important. But we don't have one on the moon.
Right. And the other thing they say is that, I mean, the Bible says that the moon is the lesser light. I mean, in other words, that it is emitting its own light. And modern science says that it's a rock that's just reflecting light from the stars that are out in space.
I'd also like to go on record saying I have no idea what the moon is. All I could know about the moon is it's a perceived circle in the sky that rotates. That's all I got.
Yeah. And we were talking a little bit on the phone off before we were recording. This was last week or the week before, whatever. And I mean, we were talking about, people, they've tried to say this footage of the the 24-hour sun and all this stuff. And I think you were the one who said to me, well, it's a fallacy to take what is going on in the stars above, regardless of what you think about that, and project it onto the earth below, right?
Yeah. You use the ground to measure the ground.
Right. Instead of trying to use certain motions of the heavenly bodies to prove the curvature of the ground, the earth.
Yeah, the whole final experiment, there was already a lot of things that were wrong with that. There's something that is infinitely difficult to explain with star trails, but really only works within the firmament. And when studying that, a lot of us old school flat earthers knew about what was wrong with the sun when you get down to like the 65th parallel. One thing is the sun and the moon, they don't appear to be, they appear to be further south than they should be. And I think it has to do with the reflection off of the firmament. But there's a series of problems with it, though. There's problems with it, and it's all firmament based. Stumbling over words trying to talk so fast.
Yeah, no worries.
But yeah, there's things we can't explain. But I mean, there's things on the globe side that they can't explain either. And I think that both of those need to be recognized and accepted. And it just is what it is. And we don't know everything. We're still learning.
Right. Well, maybe maybe the best, the best note to end the interview on is maybe on somewhat more of a personal note. Because I mean, I think you and I both know the controversy and the anger that arises from this issue. We know that people can get very, very emotional and agitated when presented to this information. So on a more personal note, what can you say to the skeptics, the people who believe in the globe? Because we both, we don't want to be disrespectful. We want to try to build bridges, not burn them down. So what would you say to the people who are really struggling with hearing, flat earth arguments or encountering people who believe in it? Like, what would you say to those people?
Use my skill to design an experiment. Just do anything you can near where you live. If you have some questions, maybe I'll address a few things in the comments when this video goes public, and I'll answer a few things. Maybe I'll reach out to you. I'll help you design an experiment where you live. I've done this for several people online. I haven't done it in some time. I've turned a couple of globies into flat earthers with lighthouse experiments that were sailors, stuff like that. You just got to math it out. Just got to math it out for what it is and just keep observing it. Now, me myself, I lived in the mountains in Colorado for some time, so I prevailed towards mountain experiments, and I have some observations that I think are brilliant in dealing with mountains. Like when I stand at tree line and I look at mountains in the distance, I see a mountain that's a couple miles away and another mountain in the chain that's 7 miles away, another mountain in the chain that's 12 miles away. Tree line lines up like a straight line at my line of sight because that's what I'm looking at.
Right.
It doesn't ever go up or down. It should be going down. I don't ever have to look down at tree line from tree line when I'm looking at a mountain that's 40, 50 miles away. It's at my line of sight. That's my observation.
Right on. That's excellent. And so, yeah, I would just say to people, even in the comments below, people are going to say what they're going to say, and that's fine. People have the right to think what they want, but I think it's always better, instead of going to the ad hominem attacks, like positively present your arguments, because that's how you can get an actual discussion going. Like if you're just saying, oh, this is stupid, this is dumb, you might feel better, but it's not going to go anywhere for either side. But if you think we're wrong, like, please, like, by all means, like, positively, just clearly. I could even say,
please
respectfully,
don't bring your ad hominem straw man arguments into the comments.
Yeah, like,
realize I was here with books and numbers. Please talk to me with books and numbers.
Exactly, but that would be my encouragement. Like, present actual arguments, so that if you do that, then we can actually soak them in, and then come back and you actually get a discussion going. And the last thing I'll say before we sign off is, people always say flat earth is this major conspiracy theory. And I think in one sense it is, to be fair, because we know there's a conspiracy to hide it. But I would just point out, in this video that we've made, everything we've talked about has been just observational, empirical arguments. It Correct. Really hasn't. If we got into history, we could go down some of those routes and we could talk about things that would be conspiracy theory. But if you listen to
I
what
can talk about Jesuit missionaries and the whole bit.
Yeah,
I didn't go that route. Yeah,
I can too. I've written books on the Jesuits, whatever. But like, my point is, if we're being fair, everything we've talked about in this is just been observational science or just what you see with your eyes. None of it's conspiratorial. It's just empirical knowledge, empirical fact.
Yeah, make a thesis and go prove it. Let me repeat it. That's what you got to do. And let's be friends about it.
Yeah, for sure. So, well, Brian, I think this has been an outstanding interview. I've really enjoyed having you on. I'd love to have you back on again sometime. So, yeah, thanks for coming on to the show.
Yeah, if we ever get back on again, I'd like to delve into more scientific laws and how they deal with space and all that kind of stuff.
So, yeah, that sounds great. So we'll figure out once we soak in all of the criticisms and the feedback, then we can come back with the mighty episode number 2. So
sounds great. It was a good time, Joe. Thank you.
Yeah. All right, guys. This has been another installment of Reform Truther Ministries with Brian Dean, and this is Joe Harper. So God bless everybody, and this is Joe with RTM signing off.
If you have been blessed by the ministry of RTM, then please consider supporting our ministry through Buy Me a Coffee and check out our website at www.reformtruther.com.